Hello, we are Chili House, and our team consists of undergraduates, graduates, and faculty advisors coming from the fields of architecture, civil engineering, computer science, electrical and computer engineering, and biology. And our goal is to develop an autonomous, swarmy robotic system that could gather in situ resources to construct and maintain a suitable environment for plant growth and to monitor crop health using minimal shipped resources. The novelty of our proposal centralizes the role of monitoring plant hydration by utilizing low-power wearable plant sensors, which can signal a modified swarmy robot from the NASA Swarmathon in order to deploy water to the plant in a 3D custom printed container. And so I'll be going over a few elements that we covered in our paper. Our first element was the simulated plant growth environment. We based our design on a modular system using lunar regolith and ethylene tetrafluoroethylene for building materials. The architecture design team worked to create a 3D design for plant containers as well as a simulated space environment where plants will grow and the robots will operate. In our paper, you'll find details about all of the support components that are housed within the self-contained payload. The water, power, air circulation, and LED lighting systems are all housed within the structure. And the novelty of this system is that it deploys from an elevated standing position with the inflatable emerging from the bottom, and in deployment, the water reservoir system deploys first to keep the heaviest portions of the assembly as low in the system as possible. Our second element was developing the software for the swarmy robots to autonomously water plants based on sensor data. So the computer science team programmed each swarmy robot to accomplish a series of tasks from an initially idle state located in the center of the dome, waiting for sensor data. The tasks are initiated once the swarmy is signaled by a sensor of a plant which is experiencing dehydration. This data is continuously generated, and the swarmy continuously evaluates whether a plant is within or whether it has exceeded the threshold. Then it travels autonomously to the pot location where the plant is when that threshold is crossed. For our developers, it is not required to rebuild every time there's a change, as all the behaviors in the primary API are written in Python. Only the changes to the ROS messaging and mapping code would require rebuilding, which allows for developers to rapidly test their code. Typically, for a robot like this to be running a behavior change on a physical robot could be just shy of an hour. However, in our environment, we can have it running on the robot in a matter of seconds. In our paper, you will also read more details about the simulated world, the physics visualization, and running the code. We created a simulated plant sensor node that publishes data just like the physical sensors would, and a visual red light indicators to flag the dehydrated plants. And we are using the robot's physics simulation gazebo and the robot sensor visualizers RViz that many prominent robots use. The computer science team was also able to break up the various tasks of the swarmy for flexibility to define specific states, for coding, for troubleshooting, and even specializing the different swarmy behaviors. Our third element was to mechanically modify swarmy robots for plant cultivation. In order to water the plants as shown, the swarmies need to have a water reservoir and an extendable arm equipped with a hose and a pump. The arm and tube are used both for delivering water and refilling the tank from the central column. Our fourth element consisted of building wireless sensors that were smaller than the commercial units. Microseries LLC is a startup founded by our sponsoring faculty advisor, Dr. David Hansen, and he recently developed a wired multi-channel impedance analyzer for tracking plant water needs via microprobes. Our goal for this project was to have a single channel sensor that can wirelessly communicate with the swarmies. So the electrical and computer engineering team worked to develop an Arduino-based device using commercially available impedance boards with sensor tips manufactured with 3D printed clamps and just standard wiring. A PinMod impedance analyzer was built, and preliminary trials have begun to measure the impedance of the soil growth media and of the stems of the chili plants. The programming of a moisture sensor will allow communication of the swarmies, initiating the previously explained watering method. For our fifth element, we focused on the 3D printing of the plant containers. The civil engineering team explored this possibility of 3D printing the containers in terms of material, system, and geometry. Our plan resulted from investigating the correlation between the 3 different but interrelated subsystems, including materials, printing system, and design. Our strategy builds on current research to develop low-cost housing and infrastructure on Earth using additive manufacturing processes. For this element, the construction team used cement-based mixture designed for construction on Earth to 3D print the containers. They conducted a stability test to choose different variables in the truncated square pyramid part of the containers, and different slopes were tested to find the stable angle that a 3D printed pyramid could hold its shape without any formwork. Element 6 was to generate real-world plant and soil data for system optimization. So lastly, you will find details about the data we collected and analyzed on the dehydrated chili pepper plants that would be used for the simulations. The data you will see is still very exploratory, but in short, you want to focus on the soil desiccation data from soil 5 in the first graph, which shows soil that is drying out versus well-saturated soil. Then in the next graph, plants 6 and 7 receive the drought treatment, and with the correlating photos, we believe that this upward trend between March 9th and March 11th is the plant preparing for desiccation and then wilting. And these exact values were isolated and programmed into the swarmies for the gazebo simulations.